Okay. Good. Oh, thanks for inviting me. Probably some of the questions that Roy did not get during this talk, he will answer during my talk, because he's the computational guru. I'm going to talk about the model. That was my contribution of the work. So I'm going to talk about classifiers, protecting classifiers from attacks. And okay. So I'm going to talk about classification. Adversarial hypothesis testing is an initial introductory stuff, then binary adversarial classification, and then a couple of approaches that we proposed in our papers, one called ACRA, and the other is called the AD-ACRA, which is related to approximate Bayesian computation. So classification is a very important method problem. It's a very used supervised learning method applied in many aspects. And what I'm going to talk about today will be probably also about spam detection. It's an important area. Most of the work has led to find accurate algorithms, but as Roy was mentioning, there is an important issue about the presence of adversaries. For example, there are adversaries who are trying to get some benefits out of this, for example, credential bank account. An example is about fraud detection. Machine learning algorithms are able to detect, have been developed to detect possible frauds, and then fraudsters maybe learn, the point is that the fraudster maybe learn how to evade them. Because the algorithm will say, look at the huge transactions, but then the fraudster can have a lot of small transactions, and that is the way they can deal with that. It was a very simple example that I made. So the assumption that we are making is behind all the work we have done is about the lack of not common knowledge. And there is this approach which was developed by David Rios, David Banks, and Jesus Rios in their book. At the end, there is the reference about it. So I'm going to talk about adversarial risk analysis. I'm not going to give a definition of adversarial risk analysis, but you will learn about it through the examples that I'm going to present. So this is the work we did some years ago, published this year. It's about adversarial hypothesis testing, which uses concepts of adversarial risk analysis. So as a typical adversarial risk analysis, we have two persons. One is defender, and later I will call this person classifier, and the other is an attacker. And we are on the side of the defender. So there is, in this case, there are a lot of hypotheses, data coming from let's say, exponential model parameter theta. You have to choose which parameter theta is, choosing between different options, essentially, in the example I will show in the next slide. But on the other side, there is this attacker which is trying to fool the defender, modifying the value which is obtained by this model. And this is the issue, the important issue here is how to make a decision. I will not enter in this detail, but the defender has to make the optimal decision based on the optimal decision of the attacker, which will base his optimal decision based on the defender, which will base the decision on the attacker, and so on and so on and so on. So it's a long chain, but we will stop at stage number one, essentially. So we have two tests of two simple hypotheses. So data coming from a model with a parameter either theta naught or theta 1. Data x is generated according to a model depending on theta, as I said, exponential parameter theta. And then there is this attacker which is modifying this x into y, trying to fool the defender. And the defender has to make a decision on theta based on the y that she is receiving. And of course, not observing the x. So there are a lot of losses of utilities involved for both of them, and both of them are trying to minimize their loss or maximize their utility. So now that was just the introductory example. Now I'm going to binary classification. We started and we dealt with the simplest case. So we have two types of objects received by the classifier. They could be either malicious or innocent. We call them the first one plus and the second one minus. And this is why this is the kind of label that we are trying to use. And this data also has some features, some covariance that we call X. So the attacker might change the axis in such a way that the defender will make wrong decisions about Y. And we have two separate stages. First of all, we have the inference about the probability. C means probability for the classifier of Y given X. So these are the beliefs about the type given the features. And then we have to make the decisions about the class assignment. We call that y sub c, and that is based on the previous PC of y given x and the utility. So this is the typical representation by using influence diagram, in which we are observing y, so this is the label which is producing the x, and then there's the utility function uc, and then there is this yc, which is the classification that the classifier has to do depending on the x that is received. It's possible also to present the problems in as a by-agent influence diagram. Here the white part is the one of the defender, the gray part is the one for the attacker, the striped one is the one shared by all of them. And essentially this is what's going to happen. So we are going to have an y, which is generating this axis, these features, and then there is an a, there is this a here, which is the decision that the attacker has to take. This is the attack. A is attack that the defender, the attacker is going to take, and that what he will do will change this x into x prime. So this is the attack done by the attacker. Out of this x prime, the defender has to make his decision, a decision about labeling as malicious or innocent, plus or minus, and there are some utilities which are involved. So, so the idea is the following. So here we have to find the class based on the x prime that the classifier is receiving from the attacker. And the first line is the usual expected utility, so try to maximize the expected utility, so let's make the decision plus or minus, maximizing this one, given x prime. And then dividing by PC of y using Bayes' theorem, we can split in two parts. The first one, which is this one, is related to the case in which the item was, the object was innocent, which is not changed, so it's important. In this approach that you are presenting, if there is an item which is innocent, is not changed. So the attacker is changing only the malicious one. And this is the, well, Roy presented already this one. This is the probability of observing a label which is positive and x prime. But for doing that, we are splitting here. So this is the probability of an action which takes from x to x prime, given x and plus. And this is the probability of x given plus, even plus. And this is one that is known. We suppose that we have applied in the training phase some classifier, and that is known. So it's important that is the probability of the untainted x. So that is important. So y. And this is over all the possible x which are leading to the x prime that we are observing. So this is essentially just mathematics out of this. Then we have the beliefs about the class distribution, the beliefs about the features, so we get them. Our classifier is giving the utility. This is the problem. The big problem is for the classifier to understand what will be the action by the attacker. And here we have to think about that. So now we have to think about the problem from the point of view of the attacker. From the point of view of the attacker, he has to find the action which, given x, the real value, and given the label y, is maximizing its expected utility. So here you can see on the top the following. So here there is a utility. What is this utility? Is the utility when the attacker is taking the action A, the original value of the label was plus, and the defender is deciding for plus, so malicious. And this is the other one, when the defender is deciding for not malicious, for innocent. So there are some computations. The important aspect here is that we have all these utilities and this probability, which is actually related to the beliefs about the classification result when C observes x prime. And we are going to put a density on this quantity, which is P. P is the probability for the attacker, probability from the point of view of the attacker that the defender will make a decision plus when he, the attacker, will provide A of x. So this is the important issue, and we put a density on that with an expectation. And this expectation, which appears here in this expected loss, is the one which is relevant for us, because we have to model it in some way. So now this is the problem for the classifier, for the attacker. Now let's go back to the classifier. So now the point is, he has to find the optimal action for the attacker. And how to do that? This is the lack of knowledge. There is no common knowledge. So how do we model that? By considering a random utility and a random probabilities. So we are going to consider random utilities dealing with this one and dealing with this one. So this is the new formula. So now we have this random utility. And what are we going to do? We are supposing that there is a finite number of possible attacks. And then we are stimulating. So we are generating from some distribution about the utility, some distribution about this expected value I said before, and then we computed for each one the realization of this, the optimal value. At the end of the day, how do we estimate the probability of going from x to x prime, given that the original value was x and the label was y, just the frequency of the time in which the simulation methods produced something which this attack was the one which was chosen. So this is the idea. Random utilities, well, they have, from the point of view of the attacker, two aspects. One is what is gaining from this game, and also the cost for an attack. So there is a gain which comes from this decision of C, and then the cost of implementing the attack. So here we are using gamma distribution for generating this cost, the first one. This is a negative value in the case in which the defender, the classifier, is not fooled. So this is in the case in which she recognizes that it is a malicious object. And then this is positive in the case in which the classifier is fooled. And she chooses to classify that as innocent, although it's not innocent. And we are assuming that if there is the original label was in minus innocent, there is no utility at all. So it's a zero. So the gain is essentially what we get from this gamma distribution minus the cost. And if A is risk prone, this is the kind of utility we are going to consider with a random coefficient here, which is from a uniform distribution. So this is the way in which we are generating utilities in our approach. And then we are going to generate as well probabilities. And in this case, what is the probability? So it's the expected probability that C classifies as malicious for X prime as a result of the attack by the attacker to X. And as I said before, there is a chain of decisions. Let's forget about it. That one, the idea here is to consider this probability coming from a beta distribution. So the probability that the class that the classifier will choose will be positive. So malicious given X prime is R, and this R is the mean of the beta distribution. How do you choose this one? Well, we look at, so we started with X, we went to X prime because of the attack. Now we go back. How many X, what are the X's leading to X prime? And we divide between the one which were malicious and the one which were innocent. And we take R as the proportion of the one which were originally malicious. And then we adjust the variance of this distribution in according to how much we want to be spread around this one. Now, let's see the spam detection issue. Let's suppose that we have n emails as bag of words. So that means that we have n words, and we are counting if there is or not such a word. 1 if there is such a word, 0 if there is not. And attached to this one, there is also a label which says the message is spam plus or not minus. So we are thinking of the email as an n-dimensional vector x1, xn of zeros and 1 with attached the label y, which is the spam or not. So now we are considering the simplest case. It's already complex. The simplest case is the one is possible only to attach the kind of adding only one word. So the word was missing, so there was 0. And for such word, it can be replaced by 1. And we are considering source only insertion. In particular, only one word at most is the one that we are going to insert. Now we have two set of indices. I of x are all these indexes such that xi equal to 0, so the ith word is not present in the original mail. And then a of x is the set of all the possible actions that the attacker can take. A naught is leave as it is. A sub I means changing the ith word from 0 to 1. So this is in one direction. And the other direction is once we have received x prime, we are interested in knowing which kind of x it will generate this one. So now we have this index, this set jx prime, and these are all the ones which have a value 1 in x prime. So there is that word, and what are we interested in? We are interested in the x's which could have generated the current x prime. X prime could have been not modified, that's why here we have x prime, or it could have been modified. So these are the ones in which instead of 1, we place 0. I remind you, in one direction we start with a 0, it goes into 1, this is the attacker. If you want to know what was the original one, we have to go back, probably, unless it's not changed, and to see if instead of 1, there was a 0. I know this is a bit tricky. And I made a mistake again. Okay, now, how do we deal with this? Well, the utility standard. Probability of y, probability of x or y standard, because we are supposing that we are just considering exploratory attacks. So all the attacks after the training, not during the training. And also we can use a classifier to estimate that. How to choose the probability of going from x to x prime? We already saw before, more or less, how it was. Random utilities as before. Now, how to choose in this case the beta distribution for P of A. So now we have to think about 3 possible cases. We started with a label which was minus, and the attacker has not changed that one. The original label was plus, it was changed by A, or it was plus, it was left unchanged by A. So this is just the ratio of this probability. These are the joint probability of observing such x type j prime and a plus or a minus. So this is the way that we are dealing with. Now, this is the huge work that Roy did in trying to compare our proposed methods with other existing ones, in particular with a naive-based classifier. So we got this data from this UCI machine learning repository, more than 4,000 emails, out of them 1,800 and more are spam. Each one of these emails has 54 words relevant, so 0 ones about them, so it's a 54-dimensional vector of zeros and 1. Now, how we did the test about the efficacy of our method? Well, we split the data in 2 parts. 75% used for training, 25% for test. But we repeated that 100 times. So every time we had, of course, a different set of data in the training or in the test. So as I said, the training is not affected by the attacks. Therefore, the probability of y and x given y are given by the classifier. And then what we have done was the following. We chose 4 different utility functions. 0, 1 is the one I'm going to show you. And a lot of different variances for the distribution, for the beta distribution of P of A of x of A. So starting from the maximum value and taking a proportion of possible value of the variance, taking a percentage of that. We did a comparison between this method, which we call ACRA, adversarial classification risk analysis, more or less. It has not a proper name, but it's something like that. And a base in terms of accuracy, utility, first false positive and false negative rates. And I would say that ACRA is more robust with respect to attacks, identified more attacker spam mails, even for larger K. Larger K means larger variance in the distribution of PA. Also, it has a lower false positive rate, and this is very important, because false positive rate means that spam non-spam are rejected as spam. And in general, rejecting non-spam spam is worse than accepting span. So that is really important. And here you can see there are, in the paper, there are many plots, but with the utility 0, 1. So 1 for the correctly classified distance and 0 otherwise. And here you can see the accuracy. So how much we get right using our work, all of this repetition. And you can see on the top, that's ACRA, which is going from 92 to 91 more or less. And what is the x-axis is just the percentage related to the variance. So it goes from 0.1 of the maximum variance of the beta up to 0.9 of the maximum variance. And as you can see on the other case, the dotted one is the naive base without attacked data, and the one in the bottom is the naive base, but in this case applied to the attacked data. And you can see that the accuracy of this is definitely worse. So this is definitely worse. And this is the false positive rate I was mentioning. In our, for the naive base is between 0.6% and 7%. In our case, as a function of the variance, it goes between roughly 2% to 3%, a little bit more. So you can see that it's working pretty well. Now, some discussion about this approach. The work we presented is essentially, we are thinking of the classifier of the attacker with a behavior which is random from the point of view of the defender of the classifier, but it is around the opinion of the classifier. We did also some work to change this, and again, our approach is quite robust. Also, there are some computational problems, because we consider just the change of one word, and also from 0 to 1, but if we have changed all the possible words, it will be 2 to the n possible attacks. How to deal with that? Like we did in our work, or instead of generating, when we compute the probability of an attack of a certain type, we will generate 1,000 data, for doing Monte Carlo, we can generate less, or there are also approximation parallelization, which are possible. Oh, so we consider also only binary classification, but we could go into multi-label. If you consider malware, we could have different kind of malware, Trojan, malware, viruses. So we could have this one and try to classify the data in one of them. Also, we could go from exploratory to poisoning attacks. That means thinking also of an attacker attacking during the training phase. Also, we consider all attacking on malicious instances, but we could have consider also attack also on innocent one. And now we move from generative classifiers, in which we suppose that we know the conjoint probability of x and y, to the case in which we just have probability of y given x. And these are the last 4 slides. Well, actually 3. And how do we deal with this one? Well, in this case, we suppose that we know only the probability of y given x. And here, as Roy presented before, we have to solve again this problem of the expected utility. And here, what is the issue? We have a utility function of classifying the class y sub c when the proof value is y. And here there is the probability of y given the true value of x. But x is actually the inverse of the one that the classifier is receiving. So the inverse of x prime, which is the attacked value. And here, to do this, we have to compute also probability of x given x prime. So the first one, utility, we specify it. This one is something that we know, is written there. And the problem is this one, probability of x given x prime. And how do we deal with this one? Roy already mentioned, but we are suppose that we don't know p of x, and how do we get now p of x given x prime? Let's suppose for different cases. The case in which x prime are discrete, finite, is even better. So we do the following. We start from x, and then we propose x tilde from a transition distribution. Then we sample x tilde from the probability of x prime given x. This is something, is the other one, the reverse that you don't know. And we accept x tilde if x tilde prime is equal to x prime. In this way, we get a sample from the distribution of x given x prime. Otherwise, if we have a continuous x prime, we cannot generate it before. By the way, the one before is very computer intensive and also very slow. These are also very slow converters. So the idea is to use the ideas from approximate Bayesian computation. So we are going to generate, like before, we are just going to generate, and now in this case, we don't accept not if there is equality, but if the distance between the value that is being generated and the one which is provided by the attacker is very close to distance, or sometimes we can use a statistic, summary statistic. This is typical in approximate Bayesian computation. And in terms of conclusion, so as I said in my presentation, I did not talk a lot about the computation, the simulation aspect, because I know my contribution is about modeling the conceptual aspects. But if you have questions on those computation aspects, Roy is here, as lucky. There are some problems about the use of the ABC method. As usual, the choice of the summary statistics is maybe critical. And then AB-ACRA, which is this one, ABC and ACRA, become computationally expensive for large-scale problems. And then there are these differential classifiers that Roy was mentioning. That is the good direction to go. And also there are some issues. So the attacker can change their behavior over time. So if they see that the defender is behaving in some way, they are changing over time. So we have to change. How do we deal with this change? We change random probability and random materials. And also, so far we have considered data which are coming from IID distribution, but we consider other data coming from regression or especially from autoregressive model. And just to conclude, the first two papers, the book, sorry, and the paper, are all that you want to know about adversarial risk analysis, work by Banks, Jesus Rios, and David Rios. And these are the three papers I mentioned. The first one is in American statistician is about the hypothesis testing. The one this one is is about the ACRA, and this one crossing finger will be accepted hopefully. It is about the approximate Bayesian ACRA, and that's all. Thank you.